Okay, so first of all, let's just talk conceptually at a high level, like what's the point of MASTAN? So you guys have used it in 181 for the factory project, and basically what were you doing with MASTAN2 in that project?
Finding the internal forces of the members. Yeah. The frame.
And did that basically allow you to size the numbers? And which numbers were you using to size the numbers? Axial force, that would give you basically P, right? Yeah. And then anything else? Well, you'd have to put the factored loads into MASTAN2, right? It doesn't know any of that. So, but what other values? Once you've run the analysis and then you're like you're looking at the results, what else is important? Flexion. So that would be a serviceability check of, but that doesn't necessarily get you the size of the member.
Moment diagram.
Yeah, moments. So then basically what you tend to look for right away is what's the maximum bending moment anywhere in your structure. And it's usually going to be right at the base for a column. And so that's going to determine, the sort of stiffness of the member and bending in the strong axis or the weak axis. So those are really the key things you're going to look for. Other things, of course, include shear. And that's a check you have to do in both steel and concrete as well. If you guys, at what point are you in concrete class right now? What kind of things are you learning? So basically what happens in concrete is when you bend it, you've got some steel and compression, or steel and tension and then concrete and compression. So that's basically what you'll do with the M value out of your MASTAN2 model if you're designing concrete beams or columns. And then shear, I guess you'll get to it as sort of like the stirrups that you design into the beam as well. So all the numbers you get out of MASTAN2 are only going to give you a piece of what you still have to basically hand calculate for each of the members. So you're going to really rely on MASTAN2 for that, not to basically generate the entire tower of members, but just focus on the maximum ones as you're going through 183, at least at the beginning. And then you'll get a sense of what are going to be the most consistent member sizes. And so you size one, you basically size 75% of the tower. And then what are some really unique, if they have unique diagrid systems or stuff like that. And of course, your W shapes only go to some limit, and then at some point, if you have mega structures, you got to actually sort of design those yourselves. So that's just sort of what to think about for like what do the numbers mean in MASTAN. The other key thing to recognize is I don't know if it was so apparent in the 181 project, but what you really should be doing in MASTAN2 is just your lateral system, because if basically what you'll have is a floor plate, and you're going to hope that your floor plate's pretty consistent from your architecture project, might not be, but when you have a floor plate, the first kind of thing you're going to do is design the gravity system, and that goes by the load patch, right? So you start with like what's the size of span of your floor slabs, and then that's going to turn into either a concrete slab or something else, but then that leads to the first set of supporting beams, then to the girders, then to the columns, right? So you guys have a sense of how you do those calculations. And that basically leads to your sizing of your floor sandwich with your girders and then your columns. And then that will go all the way down to the ground. And as you go closer and closer to the ground, those columns are taking up more and more weight. So then those get upsized. And of course, if you optimize it, every single member would be slightly different of the column as it goes down, just like you were modeling in the SketchUp model. Like those would actually be getting bigger and bigger. But of course, that makes no sense construction-wise. So you usually pick like 2 to 3 to 4 places in which the member size changes. And otherwise, you just order 1,000 of one size. So basically, you can do all of that sizing very simply just from like the SketchUp model you have, right? You can imagine that all you need to know are the dead and live loads on each floor. And if the architect hasn't done anything crazy, you're going to use the standard ones. And that's going to be an easy table you'll have very handy in 183. So the gravity system is like super easy. But then the lateral system is really about the horizontal loads, right? So you've done wind loads, snow loads, I guess, in a way. But seismic loads, have you guys done much of it all? I mean, I even haven't done much of that. I'm just taking a dynamics class right now. That's a much more tricky thing. So I have a feeling like what you're going to focus on lateral-wise is just your wind loads. And wind loads, as you can, it varies with height. It's really just a PSF against a face of your building. and then a negative pressure as well. So that's what you're really going to focus on for horizontal loads. And you can almost think of most of these, of course I'm generalizing a lot here, but most of these big towers are going to be a gravity system working pretty independently from your lateral system, which means that you can just expect every floor plate to work fine with the columns you design for, and that's just not even thinking about wind loads yet. And then you're just going to apply those wind loads to one or two specific parts of your building that are not even going to worry about gravity loads and are just going to hit those lateral loads. And it's going to pretty much take on it for the whole building. So one example of this would be like a big moment frame, either on the edge of your building on all four sides or somewhere in the middle. But you can think of wherever it is in the building, all those wind loads on sort of the prominent side or whatever side of the wall it's hitting, going to somehow eventually get to that lateral system. And it's going to hit it basically at every floor. And so what you do in MASTAN is you build just that lateral system, whether it's like a 15-foot by 100-foot moment frame or something, and then you're just going to apply wind loads on every floor. And that's going to change, of course, depending on the wind speeds. A shear wall will do essentially the same thing in the middle of a building. And to just roughly think about what a shear wall is doing for concrete, you're going to size it as just a big geometry to get your moment of inertia and your sort of stiffness and all those things. How it's actually going to resist your moments, you can basically think of it as the same calculations you're doing for a beam right now. It's going to have a bunch of rebar on one side and a bunch of rebar on the other, and then they're going to be in tension and compression. That's really how the shear wall is going to take it ultimately. So it's basically as simple as that for like the first couple of interactions with your architect. You get that tower, you model it to the degree you have now so that they get a sense of what's in it, and then you can start to do the gravity loads, so you can tell them what their column sizes are, and then you want to identify a lateral system, and that might not always be apparent. It might not even be existing in the model. And so this is really the key today, is to now have a tool to give you a little bit of a result, like an output from the input, so that you can start to iterate and figure out what is the most reasonable lateral system in the building. And what we're going to end up with for the assignment is a very simple model where I've just done a 10-story tower. There's three of them. One of them has a moment frame system just on the outsides, and I'll basically just want you to size that based on a very rough MASTAN2 model. The next tower is the same geometry, but it has a sort of H-shaped shear wall, basically where the elevators would be. And then you're going to imagine what would that size be, or what would be the forces on that shear wall if that were the only lateral system in the building. And then the last tower will have absolutely nothing in it. So then after you've done due diligence modeling the moment frame tower and the shear wall tower, you'll have to design your own. And that, of course, can be something that incorporates a brace frame. It could be a combination of the two. And you're going to make a best guess with the knowledge you have on how to accurately input forces onto that lateral system and then get the sort of resultant reactions at the base. So that's really the goal of today, okay? Of course, if you want to try doing this thinking on the tower you just built, you could do exactly the same thing. It's just going to take you forever to build that MASTAN model because it'll be like 100 floors, right? So this will be, I think as we go through just the basics or review of MASTAN, we'll just do like a single story, so it doesn't take too long to model. But then your assignment will require you to do like 10 stories of something. So let me actually quickly bring up that model just so you can see what I'm talking about. It's also on coursework, so you can download it already. Yeah, I'll do that too. You still can't open it? So this is what I'm talking about here. So this first tower has basically this as its lateral system. This one has a shear wall system in the center, and you can get the dimensions off of that from SketchUp. And then this one's up to you. So that's assignment 3. Okay. So let's see what I have here. Let's just talk about transitioning from SketchUp to MASTAN2, because obviously the workflow there is SketchUp gives you that rough geometry, and then you're going to pick a piece of that. It's never really worth your time to do the whole building, because like I said, the gravity loads is really easy to calculate. But to just grab a lateral frame out of that building and then move it into SketchUp. Hopefully this is self-evident, but when you're in MASTAN, the very first thing you do is input the nodes, right? And that's going to be basically your column, beam, joints, the places where there's connections. And the way MASTAN2 works is everything has to be typed in inches, and you're basically typing in X, Y, Z coordinates for your frame, right? And then in most cases, because we are, like we defined, these lateral frames are supported in the sort of weak direction, and they're just working in the direction they're designed for. And so we're really just modeling 2D elements. Yes, yeah, basically you have to stay consistent. Yeah. The problem is I remember all my E's and all the other things in inches, so yeah.
Oh yeah, you put your E.
Exactly. Yep. So I'll just point out that whatever you design in SketchUp, it'll be really easy to grab like a lateral system out of it, especially if it's on the elevation of a building. Let's say you have something like this. All you really need to do is isolate this piece, and then let's say that you didn't want to think so much about your inputs. Then you can take advantage of the fact that, remember, we have those locking axes, right? So we can do red, green, and blue. You can use basically blue and red in this case to get from this corner, and let's say this corner of the building or of this lateral frame is going to be your origin on MASTAN. Then you basically have to put very little thought at all into my first node is here, and then it just tells me it's 10 feet, 120 inches, and then my next node's here. And you can imagine this is especially useful. Let's say you have just a crazy line like this. Like let's assume you had to somehow input this 3D object into MASTAN. Then all you have to do is lock to the red axis, go to the edge, lock to the green axis, go to the edge, and lock to the blue axis and go to the edge. And then the dimensions of these lines is what you input into MASTAN, right? Because it's basically on a global coordinate system. So keep that in mind as a really handy way to, like, you don't even do any calculations, just read off SketchUp when you're doing this back and forth. For the purpose, for practice right now, let's just do one story of the tower in here. Like, let's just do one of these moment frames up to like just the first story. So when you open this file, you'll see that its dimension is basically 10 feet by 15-foot bays. And so this one's easy, right? So all we have to really model in MASTAN is 15 feet we just have to model this shape, right? Oh. Yeah.
How do you know, like, because there's like a thickness to the floor, like where you measure from? Like, do you measure from like top to slab or?
Well, typically it's going to be from the center line of your beam, right? And then that's ideally, it's supposed to be the same as your floor to floor height. So once you know that, then you can just stick to that.
So like measuring off of the measuring center?
Yeah, so technically your grid point will be right here, right? And it'll go to right here. But for the purposes of measurement, I'm just going to use the floor to floor height. That's going to come in, well, you'll probably won't model it to that detail in MASTAN for 183, but technically what you should be doing when you model a beam in MASTAN is, let's say this is a 15-foot beam, and you're going to assign this some stiffness and some properties. But technically, the column is like this, right? So some of this is not going to move at all, or barely anything. So technically what you should be doing is putting this dot and then putting another node here, and then the same on this side. And then we call this the effective length, right, of the beam, which wouldn't be 15 feet, it'd be a little bit less. And then this guy, you're going to assign it an E value of like way more than anything else, so that it's effectively rigid. And then when you actually analyze the structure, this is really the part that's behaving, that there's a rigid link there. But for now, that's not going to be, I mean, that's the effect on your numbers is going to be not important for now. So does everyone feel comfortable modeling this in MASTAN? So go ahead, if you feel comfortable, just go ahead and start doing that. And then if not, just keep looking up, and then I'll sort of talk it through. So the first thing you do is you go into geometry, always the very, very first thing you do, and define your nodes. So I'm going to work in inches, but the very first one is going to be 0, 0, 0, apply. And then what I tend to do is, if it's a very simple structure, I'm just going to go the fewest number of clicks and types, right? So then I'm just going to start changing my x value and go all the way across the bottom edge. So 15 times 12, 180. I'm just going to change the x value, leave the y and z what it is, type in 180, and then type in 360. So now I have 3 nodes on the bottom. And then my 360 is already there, so I'm just going to go to the y coordinate and type in now the height, which would be 120. I'm just going to go backwards on the x's now. This might sound really sort of pointless, but what's going to happen is if you're using MASTAN2 correctly, you should be trying to put in as many iterations as possible as you're trying to get closer and closer to good design. And so like literally every click will count once you're doing a 10-story building, once you're changing just the bracing members or something like that. So just this whole lab is about building confidence and sort of speed on these tools, so they feel like as if you're just doing hand calculations. So I have my 6 nodes. Of course, it doesn't matter what order you put these nodes in, and that's all taken care of on the software end. Actually, in 280, you basically have to like code the software, and so you have to deal with the fact that they're giving you any node at any point. So that's kind of fun. Next thing is to define your elements. And again, you can go in any direction, but it's sort of good to keep in mind which direction you go. But you hit from node to node, and just go systematically through your whole building and get all the pieces in. Of course, there's no need to do anything on the ground because you're going to have fixed boundary conditions on your floor, at least in this case when we're not considering soil. Now you have just a bare skeleton of your structure. The next thing I usually do is define a section. And you're lucky if it's steel and you sort of already know what it is. So I think I just said in the session what to do. So W1493, 193 for the columns, 27 by 129 for the beams. And so you just define your sections one at a time, all the different categories you'll have. So then your section 1 will be that 14 by 193. Your section 2 will be W27 by 129. Right away, you just attach these to the relevant pieces in your model. A shortcut, especially when there gets to be a lot of these pieces and you don't want to hit one at a time, you can go into advanced selection. And then you can quickly add everything that's parallel to like the X, Y axis, and then which is within a range. So in this case, if all your columns and your beams are going to be same for this activity, you can quickly grab all the columns in the Y axis and then assign that section 1. You always want to make sure you clear your selection and then grab everything that's on the X axis and then assign it section 2. Next thing you do is define your material. And it's basically going to be, I mean, it's almost never different from this, but if you're talking about concrete, you would just type in concrete and then you'd put in 3,500 here or something like that. And then for steel, which we're going to use right now, you put in 29,000. Of course, I'm talking about kip and inches as my units that I'm staying consistent with. That's your material, and then when you attach that material, you're just going to select everything and then hit apply. So you know you've gotten to this step correctly if now your lines look completely solid, right? Next step, you define your fixities. So these will be your boundary conditions. And you're going to select all 3 of the bottom ones here. And at this point, let's just assume it's all pin connected at the bottom. So pin connected means that you're just blocking or constraining its motion in sort of translation. You would add these if it was a rigid connection, right? And then now we can do our forces. So let's assume that the way the building is designed, all the wind loads of a given floor or on a given wall will the load path will get into the floor system. So since this is the bottom floor of the building, and it's and let's say the wind load, I think I had it as 35 psf. First of all, which lateral system should we really be designing first in this case? Of these two options, this guy and this guy. We're going to design the most extreme one, right? Especially if we're talking about like big members. And so it'll be in this direction of bending where this lateral system is going to take on the most, right? And that's mainly because this is the amount of wind that it's got to take up, right? So now what is just one floor of this? Well, you could just draw a rectangle like this. Select that rectangle. And under entity info, if you just grab a surface, it'll tell you its area. There's a very quick way to just see it. So 1,200 square feet on this floor. But now this translates into two separate floors, right? Half of this goes to just the ground, and then the other half goes to this first story above ground. And then as a tributary area, it also gets half of this one, right? So technically, you still are getting 1,200 square feet, but you're actually getting like this 1,200 square feet on the floor, right? So just keep that in mind. What that will really mean is that when you get to your roof, like this is your final piece of the MASTAN model, that only gets half of this. So it would only get 600 square feet, right? So 1,200 square feet. Multiplied by 35 psf. You could divide by 1,000 at this point to get it into kips. So we're talking about 42 as the number we input for that force. Okay. So that is one thing you will have to calculate right at this point. So where do we put that force? It sort of doesn't really matter. I mean, it'll give you a slight difference whether you put it at N6, N5, or N4, but not enough. So you can basically just put it at N6, like on the, just imagine it being pushed over from one side.
Do you not leave it as just a line?
You could as well, actually. Yeah, that's fine too. But think about the load path here, right? So you wouldn't do that for a girder. So when you have a floor system, you have a slab, and then you have, let's say, two beams below it, 10 feet each, that are holding that slab. It is getting a uniform load, right? But these frame into a girder here. And that girder might be constructed so it's not actually touching the slab. So you actually design this for a concentrated load, right? So that might be the same for the structure, because the lateral system isn't directly feeling the wind; it's getting it at each floor, right? Because that's not like the column next to it's feeling the pressure of the wind. Yeah.
How do you get like the section proper? When you define the section, stuff like.
Yeah. You go into define section, and then you click this database over here. It should be somewhere on this toolbar, and it just brings up a huge list. Okay. You define your forces, and obviously keep track of your coordinate axes here, but we're going to just do it in the x direction. Doesn't matter what direction, but said our number was 42. This is 42 kips of load on that floor, 10 feet up above the ground. And then you click N6. Okay. Does everyone feel comfortable with that so far? Is there anything else we need to do on this? This should now analyze, right? You've got your boundary conditions. Let's just talk about quickly what MASTAN is doing overall. If you generalize MASTAN, you're creating some sort of crazy shape, doesn't matter what it is. And then you're saying that some of these are going to be locked, and then others are going to have forces. And then all you're really finding out once you've analyzed this is where has each node moved, right? What is the force at each node, and what are each of these members doing, right? So you can really just think of all I'm doing is figuring out where is my building stuck, and that's to the ground at this point. Where are my forces? And then now I can figure out where nodes have moved if I care about the serviceability and the deflections, and what are sort of the element forces to help me design my columns and beams. It's that simple. That's really the only effective use of MASTAN that you'll need right now. So now that we have all these pieces set up, All you're going to do now is a first order elastic analysis. Just so you know, what second order means is that once you've put a little bit of load here on all of the forces, this has already moved a tiny bit. And then what second order does is it regenerates your geometry to be that shape then. And then it runs it again. So actually what you have to do in second order is you have to specify a load step. And then it's sort of changing. And actually, in most cases, it's going to make your structure weaker because as it's moving, you're introducing sort of additional moments, additional forces here and there. So first order elastic is going to be almost there for most cases. We're talking about a planar frame, so you want to make sure you select this once you're sort of in the analysis mode. And hit apply. And so basically what you want to do is get as quickly as you can to this point as you're iterating in your design in that schematic point. And so now what can you do? Usually the sort of satisfying thing to do at first is to show the deflected shape, right? You can scale that to whatever you want. Honestly, I haven't seen any team do this, but this would be potentially a nice communication tool. Just email the JPEG of this to your architect, right? Just like, this is your deflection. And you can sort of tell them you've scaled it, but like basically this is how your structure will behave, given that this is what you've sent me, right? But this is not going to tell you much for your purposes. So what's really going to be beneficial for you, node displacements. When you click on node displacements, do then is just inspect individual nodes, right? So you might want to know how much the story drift on the structure has become. So you can click on any of these nodes up here, and the number you really care about is this one right here, 0.1596 inches. Right. And you can imagine the hand calculations it would take to get to this is just like really complicated because you have so many different beams, right? The MASTAN2 is just going to save you time there. If you'll notice that as you go through N6, N5, N4, it is giving you slightly different values. That's of course because element E2 and E4 have sort of changed their length as well, right? And they're sort of deflecting here and there. But it's close enough. So you can just count on that to sort of think about story drift. Obviously, you're going to have no displacements on your fixities. The other thing you want to do is you can look at node reactions, of course, as well. If you just want to focus in on the base here, that's assuming you know that that's where the maximum moment is on the structure. Of course, here we've got it pinned, right? You can also look at shear Y, which is going to be your basic shear diagram. And you're going to look immediately for where you've got a maximum. And then you can look at moment Z, which is in the Strawn axis we need. And then you can look for a maximum here as well. So that's really all that's going to be important for now. This will tell you if the size you've input is adequate. If not, you can up that and whatever. Everyone feel comfortable with that? Okay, I'm going to take a quick break here, but then next we're going to talk about a shear wall, which you might not have modeled in MASTAN before. Yeah. I usually just use the line command.
Okay, so that's what we should use.
Well, technically here, like this is simulating the ground. Yeah, I mean technically the lower flow in this case is then.
So we just do these three, and you only model this part of the front.
So just it's moment connected column grid. Does anyone besides Connor need the SketchUp model via email? Haley, Diana?
Oh, yeah, sorry.
Anybody else?
Wait, Jared, what's the third one?
The third one is going to be you design a lateral system and then represent it in MASTAN2 and then figure out what its sort of reactions are.
I got that road. But it's only like 30 days. But I feel like I'm not doing any like cool stuff, right?
Jared,
Yeah.
is there any difference between downloading the MATLAB one and the non-MATLAB MASTAN? Like, you know, you can download just a library and run MASTAN in MATLAB.
Yeah.
Is there a difference between?
I
One
have.
of them you don't need to get.
Well, I mean, I had MATLAB, because I couldn't run.
Oh.
I couldn't run the other one.
If you have MATLAB, you have to download it.
I didn't even realize.
You can only download it.
I downloaded MATLAB. It wasn't working.
Eric, what did you use for the length of the girder?
15 feet. Yep.
Do we use our own building?
No, just use the 10-story one in the SketchUp model. I just emailed it to you. What's that?
Model mine on that.
The whole thing? Oh, you did the diagram structure. I mean, yeah, well, feel free. I mean, I really don't care. I don't need your results. I just want you to see that you're sort of.
Is it okay though?
Yeah, sure.
Yeah.
But do the entirety of your structure, right? The whole height of the diagram, right? So I know you're doing like the superstructure. You're doing this guy, right? Or on one, you should do this side actually. So what you should model is this entire thing. Right. Oh. Now, actually, I'm going to show your example really quickly when this is up too. Yeah, watch out. It's a terrible sound. Okay, we're good. So let's quickly look at at Bruno's case here. I'll just do the bottom for now. Well, let's say that Bruno wanted to model this stand. So this diagram here, right? To input the member dimensions of this, it's actually tapered, right? So what I would suggest is grabbing just the piece. Well, let's say you had.
You just want us to model.
For this example, but for the assignment,
Yeah.
when you get to the third one, do model it for the full scale 10-story tower, or choose something comparable of your own tower. For the other ones, do model the entire thing. Yeah. Yeah. So I was just doing one story just to go quickly through that. But for assignment 3, you're going to model this 10-story thing right here with all the loads, because that will give you the accurate lateral system for this building, right? And then for the shear wall, you want to model it all the way to the top. And for whatever you do here, do the same.
So how do you exactly want us to model the shear wall? Like, I'm not.
Yeah, I'm going to get to that very soon. Okay, so we're on Bruno's case right here, and we have this guy, right? But to put this into MASTAN, you're going to want to get like the accurate dimensions of this.
Yeah.
So you can of course just measure like this.
Yeah, that's what I did.
Yeah.
Drain tool?
Yeah, or I almost never use the measuring tool. I just use the line and just don't click it, but just see what's down there. It just tends, yeah, same thing. If this ever comes in handy, just keep in mind you could do this. You can, if you have a curved anything or a tapered anything and you want to just get it into like 2D mode, just orient it flat up, right? So MASTAN will let you go straight up with the rotation tool. And then now you can just say like, okay, well, this point up here is going to be these dimensions, right? It's going to be this, which is 64.39 meters in this case, and then 1.86. So that's just a way to quickly change your orientation on SketchUp, to quickly get your inputs. So let's talk about shear wall now. So to model a shear wall in SketchUp, first of all, in MASTAN, you're not going to have it in a database. So the first thing you're actually going to want to do is calculate all your properties, right? So hopefully you guys have done this recently, but really what you're going to need for the simplest calculation is just your area and your moment of inertia in whatever axis you're bending in, right? And those, of course, is just the 1/12 VH cubed with the parallel axis theorem to get the flanges, right? So that should feel comfortable for you guys. These will come in, I don't even think you need to input these guys unless you're doing more complicated calculations. But I did leave sort of what they are here as well. So all you're going to model in SketchUp, or sorry, in MASTAN2, is this, like all the way up to 10, right? Because that's technically, I mean, you can model any building like this, right? And then the stiffness here is just what's hard to tell when you have like a whole building, right? But technically, a building does have a stiffness, from 0 to 10 feet. That's a combination of all the different frames. For shear wall, what that stiffness really is that this is modeling your H shape, right? And then whatever way you're turning it is going to be the property you put into it, right? And so you have that entire property because you're calculating these guys. That's all you do for a shear wall. Now, and then so let's do that, and then let's talk about what the numbers mean at the other end of it. So actually, I'm just going to open up right now to do a full model somewhere in here. Does that make sense to everyone? Why you can just model it like that? So you don't care at all about the shape of the shear wall. You just know that it has a rigidity in one direction and a rigidity in the other direction, which is your I moment of inertia in two directions, right? Yeah, it's just going to go straight up. Yep. Actually, it's going to be 3 because then the third one is whatever you design yourself, which can just be a shear wall with different dimensions. It could be a moment frame with different dimensions, but I do encourage you to try something more inventive. Yeah. So this is a model for the entire shear wall system. Just to make it clearer, isometric. So that's what we got here. I do have one other thing I've noted on this model, which is you'll see it's this little blue thing. I don't think it's going to be necessary for you guys, but what that's really telling you is it's warping constraint. So whether these are warping together, I will show you a very quick example of what happens if this shear wall is not directly in the center of the building. Then you're going to have to account for an additional force, right? So that, obviously, you can try to model that for your third one, but there is some math behind it that I don't think you learned as an undergrad. If you do this, you put your fixity on the bottom, and then in that case, it's sort of fixed to the ground, right? So you do your boundary conditions in all directions, and then you put your forces on every single floor here,
And what I've done here is each of these would be that 42, except for the top one, which would be 21, right? Because that's just getting half of the tributary area. You're going to analyze first order elastic. And then first of all, let's look at the deflected shape. As you can expect, it's just going to be a cantilever. Let's look at node displacements. You do get your drifts, and then that's sort of the highest at the top, lowest at the bottom, as you would imagine. When you go to shear, so again, I think usually the most important thing will be your shear and your moment, whether you're looking at just the element force or the node at the bottom, or as the entire structure. But your shear is going to look like this, and so your critical number here is going to be this close to 300 kips. And then your moment is going to be this number right here. It's of course going to be a huge moment because all you've said is that there's like one beam that's holding this whole building up, right? So what does that mean in terms of a shear wall? Let's say, I mean, this is, of course, remember that engineering is a little iterative, so you got to put in some sort of shape, but then you might decide to change that shape later. But what you're really going to do is, once you have your shear wall, and let's say that you've decided that bending in this direction, like you're sort of pushing it on this side with the wind, and it's creating this moment, right? So then you've got a moment need here of 1.89 10 to the fifth. So what's really happening is you're going to design rebar, and first you're going to split it into two. So half of it goes to this guy, half of it goes to this guy. This guy does almost nothing, right, for this direction. And you're going to design your rebar system so that the combination of all of these, your area of your steel times its yield point, right, and then to the moment width of up to this guy, right? And so that's like the kind of calculation you're doing in concrete right now.
Is this a plan view?
Yeah. So that's what you're going to size there. For shear, right, we just saw that it was like 300 kips that this guy has to resist as well. Well, 150 on this side, 150 on this side. That's going to relate to your stirrup and your whole cage that you built there. But I guess you guys haven't gotten to that point yet. And then you're going to do the exact same thing in this direction. Right? So for this class, I really don't care if you got your numbers right, because that's not my point. I want to get you comfortable with visualizing this, representing this in the tool that can give you outputs to your inputs, and then just knowing that like this is the number, I feel confident in what it means. I'm going to figure out what the numbers mean in 183, or sort of as a result of finishing 182. That's going to be the shear wall case. Yeah.
So we're able to model this basically in 1D because we give it properties that the shear wall has.
Exactly.
So it doesn't matter.
Yeah. And so the shear wall basically these numbers I have here are the calculations I make on the dimensions of this, which I give in the SketchUp model with all these formulas here. And that's all you really need to do. Okay. Let me just quickly show you what you might have to consider if the building is, let's say, so this is a simple version because the shear wall is right in the center, you can say that the sort of actual force it feels is right in the center of either here or here, right? And so that just means it translates into a point force on each floor. But what if that concrete shear wall, for an architectural reason, was back here? Okay, and let's generalize this to architect puts your lateral system in a really strange place. So technically, this building is still experiencing the exact same force. Here we've got one here, and we've got one out here. So it's still feeling its same distributed wind force that you are generalizing as, or simplifying to be right in the center, right? And that's going to be the exact same thing here. So this, and then we know also that we're assuming that with load path of the design of the building, it does get to here eventually. So it's still going to feel the same point load that you're going to input on each floor, but it's also going to feel a moment, right? Because technically the lever arm is right there. It's going to be your H, whatever, right? So all that changes in your model for MASTAN. And first of all, I'll say that this is where you do have to specify that these H's, as they're blocking onto each other, are not going to warp from each other to get the right values here. But open offset model. So the only difference in this guy is that I'm also modeling moments. Okay. And those moments are basically the same force, but then times whatever distance this is, and that's the geometry of your building. Okay. And again, it's just half of that on the highest floor. So what that does to your results, let's just look at the very bottom piece here. So notice this, its shear is exactly the same as what it was before. That's what it's telling me here, like that 300, right? So it's still this 150, 150. Its moment is also exactly the same as it said here, but it has this twist, right? It has this twist, which was the 0 value from before. And technically, so you do have to do some calculations on what this means, because this twist gives you a little bit of extra shear to take care of or to consider, and a little bit of extra moment. But if you can imagine that I have this H section right here, and if I'm turning it this way, that's kind of as if this piece was rotating in this direction, and this piece back here was rotating in this direction, right? To sort of counteract the turn. Or that's the experience it has, so the resistance is going to be in the other direction. So it's actually that the two flanges of your shear wall are now experiencing a very different kind of force, right? And so what happens is, if this is the way your building has turned, and you're putting a wind on this anyway, this wall is going to feel a lot more work, because it's this compounded with the turning that it has to resist. Whereas this one actually has a little bit of force canceled out for it, right? It's resisting the overturning of the straight force, but the turning of the entire shear wall is actually helping it out a little bit, right? So then what's going to be the most important thing you design here? It's going to be this flange, right? Because it has the double impact. Probably not going to have to worry about that in 183, but that's just something to keep in mind, that if torsion ever comes up as a topic, of which it might, these are the sort of dangerous things we're talking about, where you're getting a double effect from the basic bending moment you've already calculated, and then the effect of torsion on one specific part of that piece. Okay. Yeah.
So when we're modeling this in MASTAN, I saw that you only put the wind in one direction, but like, don't you have to look at bending about both axes?
Yeah. So in the case of the, so first of all, you don't have to do that in this assignment, because you're just going to focus on the most intense moment frame, right? But what you do is, in this case, it's the same geometry. So you just save two different MASTAN files, and they just have different forces. So one of them is going to represent this guy, which is taking up the wind force. And actually, I didn't make an error here. You're in this case, you would want to split the overall force in half as well, because half of it's going to go to this moment frame, and then half of it's going to go to this moment frame in that direction, right? So just split the area one more time. But then you're going to do a completely separate model, completely separate representation for bending in the other direction. And so the geometry just happens to be the same, but then you might design this one differently because it has a different set of forces.
So there are going to be 6 MASTAN models.
Yeah, but that's in real life. If you were designing this whole building, for this assignment, just do one for each tower, one representation, right? And I'm telling you to do the worst one.
You only have to do it in like one direction.
Yeah, do it in the direction which would be the worst, which would be the weak axis, right? Well, actually, maybe that's not going to be immediately clear, because in this model, the axis is going to be a force coming from this side, right? But it's going to be a little bit less force, because the width of the building is a little less. In this direction, it's stronger, but you've got more force. So I couldn't actually just say right off my intuition which one's going to be sort of the critical moment to design for.
So can we just pick one?
Yeah, just pick one for now. But just know that, like in 183, you will want to check that kind of thing, right? So what can you do for the third tower? I'm just going to show one example if you want to go this route. You could do this, right? So all I've done is I've created sort of like a chevron on each floor. What you'll notice is that decreases significantly the amount of forces that the lowest column experiences. And so what you've done is you've sort of taken away a little bit of your material from your vertical column, vertical member, and then you're sort of adding these bracing members. And that could be a really good solution if you're tight on space. Any questions overall?
You go back to the sketch.
Yeah.
Go over how you got the tributary area like this. So is the wind coming in the green axis direction on the first tower?
Well, it can come in any direction, right? And you're just going to size the worst case scenario, because that's your sort of first reality check. I'm still, in the grand scheme of things, this is like the first week of what you get from your architects. You're eventually going to size everything, lateral load in both, lateral system in both directions. But as a reality check, you're just going to see what the biggest members are. And so in this case, we're going to focus on this member because it's going to get the most wind force. Basically, the skinny side of your tower is going to be the one you want to start with, right?
Yeah, because it's the most area is
Yeah.
on that.
Yeah, and in design, you're going to be the most constricted on how far you can go. So, like, for example, this tower is screwed, right? Actually, it's screwed in both directions because it's a square. But imagine that same, you don't have the affordance of a sort of wide width to your bending moment, right? You can't deal with moment by having a lot of compression in one column far out and a lot of tension in the other one. You're going to actually have a lot of bending moment on each column.
So for that tributary area, we just take like the side that we're hitting half it.
Yeah, so let me just quickly show what the exact one would be. So let's say that we want to figure out what force do you put on this guy. That's a node in MASTAN. And what's the point force you're going to put onto that? It's going to be basically this.
Yeah.
Right. And of course, if this was placed somewhere else or there were three of them, then one of the things you might decide in your option is to add just more moment frames and just get a sense of proportionally what does that do to your members. You're going to be dealing with a lot of situations where you're trying to downsize things, right? It's just like you say to the architect, there's no such thing as a W 5 billion, right? And so you got to break that down into multiple systems, into multiple frames that are acting, extend it as far as geometry will allow you to, add bracing where you can to increase the stiffness. Those are the only choices you really have once a tower is set in its geometry. And so whether you like it or not, you might experience a point in 183 where you're in one night, you're just cranking out a lot of these. Every single one, you're just changing one slight thing. Maybe you're just increasing the size a little bit of the geometry. Maybe you're adding braces here and there. Obviously, you want to be economical, so sometimes you might just be taking pieces out of something that already works. But that takes time, and that takes feeling really comfortable with MASTAN2. But if you understand what the reason for that is to make something that would have been way harder if you were hand calculating this into a manageable task that you can iterate on MASTAN2, then you'll become really effective at sort of designing at the pace of the architect. And again, MASTAN2 is going to be about your lateral systems, which is your very first consideration for these tall towers. Any questions? Yeah, Caesar.
Would there be a force on the opposite side of the moment frame?
Yeah, technically. Just assume that the number I gave you is a combination of both. So the 35 PSF is just going to be the force you experience. What you'll probably do in 183 is like some of the members of the class will actually go and do like a really comprehensive wind study that then everyone can have. And then another group will do like a whole foundation study, and then another group will do a seismic study. And so you'll have all these numbers to play with your load factors. But it all goes into basically this, which will be different for every student. Okay. So in general, what do you guys feel about this? I mean, obviously this is one of the first experiences you'll have at Stanford designing structure, right? I mean, besides like King Cho's little factory. So if now that you see that this is really what it comes down to, this kind of, working with your hands, this kind of methodology, this kind of rote repetition, I mean, is that exciting to you guys? Do you feel like this is empowering, that you have some design language that you can communicate to the architects? And hopefully, above all, whether it's SketchUp, MASTAN2, and in the broad scheme of things, I think next week, oh cool, next week we're gonna do hand drawing. So that's just another language, another tool you'll have. All these things are gonna hopefully just be empowering you guys to be able to influence these designs and to make them realistic. Okay. So we're doing MASTAN2. I will send an email out about, but we'll probably just be upstairs in the green atrium. That's where there's sort of like lots of tables. Don't feel like this is going to be the kind of studio where I force you to, put $100 into like nice materials. We're just going to use basic paper and pencil. That's fine. The point is not to make it look pretty, but to make it look accurate. Okay. And then so that will be another skill. We'll look at some spreadsheet work after that. And then basically by session 6, 7, 8, 9, we're going to look at we're just going to be pounding you with challenging architecture, and you're just going to think through that. And hopefully by then you feel comfortable with like this wide array of tool sets, and that you can actually, turn your thoughts into real designs. Okay, so that's the whole point of this lab. So if you have questions as you go through this, technically this shouldn't take you long at all. The longest thing literally is going to be just putting in the notes, but that's specifically there to just get you to practice, like what's the fastest way to type through this. You don't want to be bogged down by that in 183. And then just be as creative as time will allow you to for this one. But I really want you to realize that this is the same building with the same overall external forces, and what you're changing is exactly what your responsibility is in 183. Right? This is the architecture. They've just given you the most boring building in the world. And how are you going to deal with the structural considerations, but also maybe come up with something creative and inventive that really contributes to the architecture. Good. Cool. Well, feel free to stick around and just get started if you just want to get it out of the way. Also, if you want to just assume like I know how to do this, I'm just going to play with this right now and just think about this. And if you run into a SketchUp problem, feel free to ask that sooner than later as well. But assignment 3 will just be those files on the coursework. It'll be the SketchUp model. The only thing that I'll see on the SketchUp model is your third design, right? And then the 3 MASTAN models.